Thank you. Good evening, everybody. I'm a mechanical engineer, so I have to speak of engineering. In particular, I am assistant professor of turbo machinery and engine design. Accordingly, my talk of today is about efficiency and energy, with a special target that want to lead you from, in an ideal way, from the regulation to the research. So my presentation of today starts with a brief outlook of the energy consumption, focusing on different origins of the energy consumption, especially related with the pump world. Then I'll lead you to a brief outlook that starts from the components, so the pumps in our case, and try to focus our ideas not only on the component, but to a system of components, so to the pumping systems. Then I'll give you some ideas of how is it possible to improve the efficiency of pumps, and in particular on the generally spreaded pumps, so not special realization, but common commercial pumps. And before to show you an example of current research in the pumps world, I'll conclude my presentation with a brief portrait of the market trend and the development in the pump technology. This quite complex imaging is a portrait of the energy consumption in the European Union. So at the center of the figure, you can see the total energy consumption. As you can see, we are speaking about of 20,900 terawatt hours per year. So if we concentrate on the outer circle, complete circle, we can see that more or less more than a quarter of it is the red region, so the region of the heat production, whereas another important slice of all the energy consumption is the gray region, that is the fuel directly burned to power vehicle and in general for transportation. Of course, there is an important fraction, more or less the 25% of energy dissipation in the conversion of the energy, that is the light blue sector. And finally, there is another important slice of energy consumption, that is the energy that is transformed into electricity and then used and consumed in the electrical form. So what about pumps? Where we are? You are in the broken line, red broken line here showed. And in particular, the electricity consumption is about 13% of the total energy consumption in the European Union. Almost half of the consumption needs to power electric motors, and in turns, pumps requires about 22% of the energy used in the electric motors. So the numbers, we are speaking of about 300 terawatt hours per year. This is the reason why legislation, standard, and directive focus on the energy consumption and, of course, on the energy efficiency of the device, of such device. In particular, if we consider the share of pumps energy consumption, first of all, we can refer to the three likes imagine on the right, where there are the different classification of pumps, and we can distinguish between rotodynamics and positive displacement, and the rotodynamics say turbo machinery, We have the classical centrifugal mixed flow axial, and again, in the centrifugal field, we can distinguish from the single stage realization of the multi-stage configuration. And focusing again on the single stage, we can divide it in double entry pumps or single entry pumps. So, that said, rotodynamic centrifugal single stage, single entry pumps represent almost the 50% of the total energy use of pump in the European Union. In particular, if we focused on the commodity types pump, so the mass-produced realization, say water pumps for commercial buildings, drinking water, and so on, these that are colored in blue, and you can find the special type in the table on the right, these pump types alone represent almost the 46% of the total energy use of pumps in European community. So this is the reason why direct legislation focuses mainly on these types of pump. So the study, the preparatory study of the directive commissioned by the European Community used the methodology for evaluation of energy-related products, which implements the analysis of life cycle cost of each product, and in particular with pumps. The results basically said that, of course, reduction in the weight of the products, so lighter pumps, is something that manufacturers would research, but this and also the production, the distribution, and the end-of-life phases are not the relevant phases that affect the eco-environment. They are not comparable in magnitude with the use phases of pump that is responsible for the greater eco-impact of the pump usage in the world, in the European community. Accordingly, this justifies the focus of energy efficiency as the primary means for improving the eco-performance of pumps. Like all the mechanical components, also pump have an efficiency. The efficiency is, of course, the useful effect in terms of energy divided by the energetic cost of this useful effect. But we can also represent this ratio as the useful effect divided for the same useful effect plus the dissipation within the components. Accordingly, to increase the pump efficiency, we have to reduce the energy dissipation. It is a matter of fact that in most real applications, the big number of pumps spend much of their working time far away from their design point. This implies that not only they are not able to reach the desired performance and to consume the desired power, but also the efficiency in which they use the energy is quite different. This fact have to be accounted, of course, by the legislation, but also by manufacturer. In this sense, the House of Efficiency scheme, where is the light, try to tackle with this issue, and in particular, it consider for the certification of the pumps not only the best efficiency operation, but also a partial load operation and an overload operation. So a pumps to be sold in Europe or imported in the European Union have to have an efficiency curve that is able to cover the so-called house of efficiency. However, this is the pump, but the pump on itself it does nothing. What the customer, the user, are interested in is the pumping system. So a system of components. As example, at least motor and mechanical transmission, the pumps itself, of course, a piping system, and so on. So also the pumping system, like a component, has his losses and his efficiency that once again is affected by the dissipation. Now, however, losses is not only the loss of the pump, but is the loss in the motor, the loss in the transmission, of course, the loss of energy in the pump, in the piping, and so on. So what the equation of the system efficiency say to us is that to increase the system efficiency, so to reduce the energy consumption, we have to work on each one of these terms, so on the to reduce the dissipations occurring in each component. But what, and of course, this is what the directive, the regulation are trying to do at now. But what it is not explicit in this relation, that it is not always important that we have the best component. It is important that we focus on the system's results. So the collection of all the components have to produce a result that is the best results for us. So what is the next level of the legislation? It is difficult to predict the future. However, I think that the way of thinking on the system instead of that of the single component, if we will not be the future in terms of legislation, as to be the future in terms, once again, in terms of the users. In particular, I'll show you some numbers that I think that are self-explaining. A correct specification and design of the system in which the pump is installing is able, according to stakeholders managing the data of today, to increase the energy savings from its own of the 10%. So we have to change nothing in the technology, we have to do nothing in research or change our way of production. We have only to use the right component in the right place. Something similar to from the correct selection of pumps. It is not decisive to select the highest efficiency pumps. You have to select the pumps that performs at its best efficiency point close to the requirement of the system. A correct selection is also able to save an additional 4% of the energy consumption. And even greater, the control of the systems. For example, the use of variable speed drives can make in some system energy savings greater than 50%. However, it is estimated that on the average, a better control of the system can increase the saving of energy of about 20%. And of course, a certain effect also depends from the correct maintenance of the pump. This is a two-phase medal, so correct maintenance is not only the periodic maintenance of the device, but also the better installation, of course, to avoid vibration, cavitation, and so to reduce also the wearing of the different components. It is not always correct to sum together all these terms. However, to have a qualitative trend, if we perform the sums, we see that we are able to save more than 30% of the energy consumed by pumping system without doing revolution in the pump technology. So the conclusion of this slide is that beyond the pump itself, large energy savings are to be found by looking at the system. However, from the hydrodynamic point of view, what we can do to improve the efficiency of this type of pump, so in particular of single stage and suction standard industrial pumps, what we can do in a cost-effective manner, so without speaking about top-level research, but with solutions that are in the hand of all the European manufacturers. First of all, we have to consider that possible gain of efficiency strongly depend on the type of the pumps and of the absolute type of the pumps. In this diagram, you can show in the ordinate the specific speed, so different type of pumps, and you can see how efficiency change from type to type. It is interesting that if you look at the different colored line, these reflect the increase of the efficiency that you naturally have when you increase the pump of size, the size of pump. Of course, first of all, we have to account of it because increases that are feasible on a certain size, it is maybe not feasible on a different pump size. That said, it is a matter of fact that most of pump manufacturers, almost of European pump manufacturers, have the know-how to perform an hydraulic correct design. And the main proof of this is if we look at the history of centrifugal pump efficiency. And looking at the data, at the best technology in the sector, we will see that it is something about 30 years that efficiency of this type of pumps doesn't change. So it is a proof that the way of hydraulic manufacture, the way of design of hydraulic manufacturer is a correct way. So what is practically attainable to increase the overall efficiency is mainly influenced by the surface roughness, so technology of production, by the internal leakage from the impeller to within the casing, and of mechanical friction. It is fundamental in this sense to perform a breakdown analysis of pump losses. The main losses considered are the hydraulic losses, the volumetric losses, so the backflow across the gaps, and the mechanical losses. So the final efficiency, overall efficiency of the pump is split looking at the different contribution that decrease the efficiency from the ideal 100% to the actual efficiency. As you can see, independently on the pump types, mechanical losses stay almost constant and are, as a percentage, quite low. So these are not capable of significant reduction, although you don't want to spend a lot of money with very high, very costing technology. Accordingly, the main factors that affect efficiency are the surface roughness, that is responsible for the hydraulic losses due to friction, and the different gap clearance, that is responsible for the volumetric losses. So, it is interesting to know what happened if we change the roughness of the wetted surface of this device. This is an ideal computation of a model, but it was quite well validated with experimental results, so it is able to give you at least some trend, but also, I think, some quantitative trend. The black line is the efficiency, the maximum efficiency of a certain, of a fixed sized pump for different types of pump. This is when the surface is perfectly smooth. On the other hand, if you look at the red line refers to a surface roughness that is comparable to low quality of manufacturing. The orange line is the representation of the widely eroded or incrustated surfaces. As you can see, there are big differences from the worst case and the ideal case. For give you a number, surface smoothing of low quality inner surface can lead to a 5% minimum efficiency gain. Obviously, this at the optimum specific speed. So, whereas if we consider the maximum efficiency gain, it can exceed also the 20%. Of course, smoothing of the whole pump is a very cost-intensive process. This block scheme show you the expected increase of the efficiency if we smooth the whole pump, but it tries also to show you the different contribution due to the smoothing of the different piece of surfaces of the impeller, of the casing, of the dilute. What we can see, if we come back to this representation, is that if we smooth the internal fluid passage, so the vein passage, we are able to increase the efficiency, especially for high specific speed pump. So, say, design that tends to mixed flow and axial configuration. But this difference stays almost constant if we consider the low-speed machine. On the other hand, what becomes very important as the specific speed is decreasing and the effect of the friction in the outside surface of the impeller. So the friction between shroud and hub disc with the flow that moves outside on the impeller. Accordingly, what we can do for pumps with lower specific speed, we can only smooth a part of the outer surface. If we start the turning operation from the outer diameter and we proceed towards the center, the eye of the pump, we can reach an interesting efficiency improvement quantifiable in more or less 5.5% when you turn only the first 40% of the external surface. And if you limit the turning operation only to the first 20%, you are still able to increase the efficiency of more than 3%. So there is no need to smooth the impeller at smaller diameter where the technological operation is, of course, by far more difficult. But you can stop it only at the outer surface. And as a conclusion, smoothing only part of the impeller front and back shroud is a very efficient procedure. Finally, we have to speak about the gap, the tip clearance, so the backflow from the delivery of the impeller to the suction of the impeller. This numerical prediction take as a references a gap of 0.6 millimeters, and as you can see, if you reduce this gap to 0.5, 0.3, 0.1, you are able to obtain this efficiency increase. The contrary, of course, if you increase the gap. However, the reduction of clearance can improve the pump efficiency. For instance, you are able to obtain an almost constant, so independent of the pump type, increase of the efficiency, passing from a gap of 0.6 millimeters to 0.3 millimeters. With this in mind, we can discuss what the market trend, where the market is going, and how this is connected with the development in pump technology. we can see that there are several positive trends which lead to a reduction in energy consumption, in particular, with particular reference with the types of pump we are discussing. First of all, there is a trend in greater sale of pump with pressed stainless steel or plastic impellers. Pressed stainless steels or plastic impeller signify smoother surface, so this is a key solution to reduce the surface roughness that I have talked about before. Once again, there are variable speed controls incorporated integrated packages. They are able to give large energy saving, often larger than that obtained from improving the pump itself. This European pump estimate, it is not very recent data, however, it is an indication, show that in the different types of pump, the alignment with this type of solution start to count numbers that are not zero. Also, there are trends that show that are in the market, there are pumps available with built-in condition monitoring, and this facility can increase the gain in energy saving due to the maintenance of the pump. And again, looking at friction, especially for the larger pump realization, there are some products that have friction reducing coating on the cast iron volute. So again, following the trend of reducing the smoothness, increasing the smoothness of the surface. So how the academia and the research can help pump manufacturer? I'll show you only an example of current research on pump. It focuses on the CFD modeling. Why CFD modeling? Because CFD is now a very cost-effective and in absolute effective tool to predict performance and flow features within all the device managing flows. So CFD modeling to hide the design of steel sheet multi-stage pump. This realization, so pressed stainless steel multi-stage pump, many times called simply vertical multi-stage or compact design pumps, have as main advantage that they are now a reliable and cost-effective technology. And as I have already said they also feature a quite smooth surface, so they are potentially able to reach high efficiency. Of course, they have also some drawbacks, mainly linked to the unconventional shape. So the geometry of the rotor of the impeller is two-dimensional. They have a wide annular chamber that connect impeller and rotor channel, and the problem is that these unconventional shape are not well documented in the literature, and there is not so many scientific know-how on the behavior and how to improve the behavior of these quite unusual, from the hydraulic point of view, designs. So what we have done is to suggest a very simplified model, so especially focused for the industrial application, that consists in the model of only a single passage of only one stage of the multi-stage machine with a steady-state approach. So neglecting all the main details of unsteadiness and so on, that of course are now possible to calculate in the research field, but that is not so easy, this is calculation that are not so easy to perform at the industrial levels. And we have suggested also a procedure that is able to project the results of this simplified calculation in the performance of the whole pump. These, for example, are the results of the calculation considering a swirl-less single stage, single passage. As you can see, the results are just as they are quite satisfactory in terms of performance and also in terms of power coefficient that is strictly related to efficiency. However, with the introduction of the correction we have suggested on the basis of our research, we were able to increase the prediction. Of course, this is one step of an ongoing research that is aimed at producing at the end a complete methodology for the design, for the industrial design of this type of machine. So this is an example of how the academia can help manufacturer in dealing with the problem that they are. Thank you for your kind attention. I have finished.